The next speaker is Joshua Cranmer from Mozilla, and he's going to talk about semantic browsing of source code using LLVM.
So first off, I would like to thank you all for coming. This is basically a talk on a project that I was working on this summer with Mozilla. It's called the Dehydro Cross-Reference. It's a semantic source code browser, so it's designed to be able to let you browse your source code more effectively and get a better understanding of your code. So first off, why would you need some sort of source code browser? And the answer is because large code bases are very problematic to deal with. For the basic example, Firefox is over 8 million lines of code. And just trying to understand that is impossible for any one person to do at any point in time. Also, many very large code bases also have problems that they have multiple languages. So for example, in Firefox, most of it's written in C and C++, but a large number of it is written in JavaScript, and there's even some portions in assembly. Or if you think about LLVM and Clang, where they use a lot of table gen for ancillary definitions. There's also another problem that you get, which is the problem of generated code. One statistic I ran up said that about 5% of all of Firefox's code is generated at runtime and not by the compiler. So if all you ever do is just look at the compiler, just look at the source code that you get in before it runs through the compiler, you're never going to be able to get all this generated source code. So sometimes, especially if you think about just trying to find a definition for method, this method might not actually be defined anyway in the original source tree. It might be automatically generated, and the definition is in the generated code base. So you have to also be able to search generated code. You can also read all of these other statistics. These were all generated by DXR. I used the SQR database to basically count all this stuff up. And I'm quite sure that there's a lot of inaccuracies in here because this is several months old already. So existing work. Source code browsers are nothing new. Linux cross-reference has existed for, I believe, over 10 years already. It's the most similar thing to what DXR is. It's basically, it goes through all of the code, and it basically runs code to HTML first, but it also generates links for every single identifier in the code base to try and allow you to grep. Effectively, it's a glorified grep. It knows where all the functions are defined, and it can give you that problem. You also have tools like ctags and Doxygen, which can help you with understanding the source code base, and they are similar in this environment. However, these have lots of problems. First off, most of these are based on basically grep. And unfortunately, grep does not work very well with macros. And I'm sure anyone who's worked on large code bases knows that macros are extremely prevalent. You have problems where your function definitions may be hidden inside a macro. Other times it may just be that you just can't parse it because it looks like there's four function definitions, but there's only one on that line. These are not hard to fix. You just have to run a preprocessor. Except on really large code bases with highly convoluted build systems, running a preprocessor on every single file is not exactly easy. The more problematic problem is that for the most part, most of these are primarily designed to work with C. So they generally use a simple function name to find everything out. And if you're in C++ code bases, you can have lots of really common method names which have lots of implementations which you don't care about. The standard example I like to give is Firefox has 700 functions that are called init. And at any one given time, I mean, sometimes you might care about some of them because they're virtual method implementations, and it actually is legitimate that you can call several different targets, but the largest one of these is only 40, and that's the most extreme case. Most of the time, there's only one or two methods that you're actually looking for. So if all you're doing is just know that this function is called init, you've lost a lot of information. So the design of DXR is DXR gets around that by saying, look, someone already solved this problem. That's the compiler. Let's get the compiler to instrument everything and tell us what we need to know. So Clang is divided into three major parts. The first part's the compiler plugins. I say compiler plugins because it's designed to work with multiple languages. So you have a plugin that can understand, for example, in Mozilla, IDL, the interface description language. But there's also another plugin which understands C and C++. In this case, we're using Clang. After all the plugins run, we have an indexer, which takes out the results of all of the compiler plugins and combines them into one large database. And from that database, you generate a web application, which you can use to browse your code. So the final output is something that will look very similar to LXR. As I said earlier, we also want to try and have support for multiple languages, because most very large code bases have several languages. The final thing is it's also designed to be modular and extensible. One example plugin that I have implemented already is we have code coverage. So if you have test suites, you can just you can compile with the code coverage stuff, run the test suite, get the results, and then after you run the plugin with the code coverage, it will be able to say on your annotated output, here are the lines that were covered by your test suites and here are the lines that were not covered. So first, the compiler plugin. As I said, we're using Clang. We used to use GCC, but we switched because there are so much more better features by using Clang than GCC. The plugin right now hooks into 3 major components. We hook into the preprocessor callbacks. That allows us to get all the information we ever care to know about the macros. Firefox has something like 40,000 macros, so macros are very important. We also hook in the diagnostics client, so we can record all the warnings in the code base. I don't recall all of them off the top of my head. I think something like 5,000 warnings. And we also run the AST consumer to get the meat of what we actually are looking for, which is to say all of the function definitions, declarations, class inheritance hierarchies, everything that's called, all the references, etc., etc., etc. Now, what we do with all this information is we basically ask, first, is this a feature that we're actually going to care about that a user might want to know? And for this definition, I am using, is this actually correlated to an actual token in the original source file, in the original source tree, or is it a token that comes from the build tree? So is it something that's coming from generated code? If it's not, we don't care about it, we move on. If it is, we then record all of this information into a per file buffer. In this case, we're indexing information not by the translation unit that comes out, but rather by the file in which it's originally included. So if you have a header file, it includes so if you have a header file, it only generates the information once when you include the header file. Because we often run compiler builds in parallel, and we need to worry about stomping on each other when you have parallel builds, we use a little trick where we use the output file name we write to has a hash of the contents included as well, so that we guarantee that we don't have any problems of, so we can guarantee atomicity of writing out the output files. The second portion here is we have the indexer. This runs after all the compiler builds complete, and this combines the results from all the plugins into one giant database. The reason we don't do this at, say, link time or anything else is because, again, with really large programs, it's never guaranteed that you're going to see everything at one compile time, at one link time stage. In fact, if we want to look at JavaScript code in Firefox, there's no way you see you don't see JavaScript code anywhere at compile time. All you get is after you run the code and you see the output where all the files are located, and then you can index those files afterwards. So you have to do the full indexing and combine every information after you run everything. So what sort of stuff do we do in the indexer? The most important thing is we map our declarations to definitions, because unlike most programs, we do not use the simple unqualified or even the qualified name as the unique identifier. Rather, the identifier is the qualified name and the location where it's actually defined. This also allows us that we can distinguish between different versions of static functions which may happen to have the same name. We also do some limited whole program analysis. So for example, we create the type hierarchy, so we know which classes inherit from which. And again, for something like Firefox, half of our types are defined in IDL. So we'd rather say this interface is not actually the C++ function which is in this generated source code file, but rather it's from the source code IDL file definition, and refer to that instead of the generated code. Also, we need to create the complete call graph. And to create the complete call graph, we need to know what are all the possible virtual method implementations for any method. And the way we do that is we need again, the complete type hierarchy. We need to know which methods can we implement any given virtual method. So we have to do that, again, at this final compile time. As I also said, we also choose this time to resolve all of our cross-language entities. So for example, we know this IDL method corresponds to this C++ method in the code base, or this JavaScript method compares to this IDL method as well. And finally, after we get all this information together, we remove all the duplicates, we sanitize all of this data, we finally create the complete annotated source and also the auxiliary database. Finally, when we have that, we now have a nice, easily usable web app. The web app is using an SQLite database for the backend because for a database, anyone who knows databases pretty much knows SQL, so it's the de facto standard. Like LXR or other sorts of tools, we have statically generated HTML files rather than trying to do the code to HTML conversion on the fly. And finally, when we retrieve all of the information, we use JSON for all of these queries. To give you an idea of how large this is, the total generated database for Firefox, which, as I said earlier, is approximately about 300 megabytes of code. The total output database is, at this point, I believe, about 800 megabytes. So let me give you a little demo of the web app. So this is basically what it looks like. We basically have a search bar at the top. We have the source code file on the right. And what we also have, which is different from many other tools, is we have a sidebar on the left. And this sidebar tells us every single function, every single variable, every single class that's defined in this file. So if I were to click on any of these function names, it would actually go to the location where that is declared or defined in that file. And also, again, since DXR knows about, since it runs from the compiler, it can understand everything that's being hidden by macros. So in this case, we have the local file. This method is actually being declared within this macro. So grep won't find this. It won't not tell you that this is actually located here. This is one feature that DXR has, which I have not seen commonly implemented elsewhere. Also, inside the file, you can click on many of these things. So, for example, you can click on the macro. It will tell you what the macro expands to. If you click on a function, it will tell you, first of all, it gives you the full name of the function, the fully qualified name, including namespaces and classes. It unrolls all of the macros that you may see. In very large code bases, you tend to have a lot of macros hiding stuff in definitions. So, for example, this NSAC string is actually defined to be NSAC string internal via a macro. And it will also tell you the definite where this method is defined and all of the methods where it's, in all of the places where it's declared. Because several times functions can have several declaration places. And if you want to know which header file do I have to include to get this function definition, well, just include ns-localfile Unix and you will get the declaration that you need. It also will tell you all the references. So this tells me every place in the code base where this function is specifically referred to. It can also tell me, if you choose to enable it, it can also tell you everyone who calls it and all the functions that it itself calls. And also, by using the various AST features, it knows about virtual methods. So it can tell you, if you call a virtual method, it can tell you, well, it's going to call one of these methods, but I don't know which one at compile time. It's chosen at runtime. If you have a virtual method, it will also tell you all the methods that we implemented, which is very helpful if you've got a, for example, in this case, you want to find, this is the open content stream that I called, and I want to figure out which one of these am I actually going to be using. Is this the opening content stream for an FTP stream, or is it going to be for a data stream, HTTP? What is it? For classes, you get more stuff. You can get all the members of the class. So for enums, it can tell you the location, it can tell you the values of all the enum constants. It can tell you all the variables. It tells you all the functions that are defined. And also, more importantly, it can also tell you the complete hierarchy. So in this case, this is inherited from NSFrame, but it also inherits some other interfaces indirectly. I can also tell you, because I've created the complete type hierarchy, all of the places in the code base that inherit from this. So I can tell you all the derived classes, both direct and indirect. One of the features I mentioned before is we collect all the warnings. So what happens there is in the source file, right next to the line number, we produce a little icon which shows you when you compile this code, you get a warning. And if you hover over it, you can see what this warning is. In this case, it's because someone changed the code and forgot to remove the place where this variable is defined. And as you can see, this is another place where we're hiding more variable definitions under macros. Mozilla has a lot of this, unfortunately, which is why you can't just use LXO or MXO or any of these tools to look at it, because they don't understand macros well enough. In addition to just looking at information, you can also do a lot of searching. So in this case, you can search for several types of semantic searches. In this case, we're searching for which classes inherit from this interface, NSI frame. And there's about 50 or so classes, and if you scroll down, you can see them all. You can see where those classes are defined. You can see whether that's a direct or an indirect inheritance. And we'll also show you the code where it's done, too. So you can click on that line. It gives you a little bit more idea of the context of the code in which it occurs. You can also do searching. You can also search for reimplementations of a method. So who implements this file called NSI file append? Well, there's only one implementation for this interface in this code base, at least in Linux. If you compile it on Linux, there's only one implementation. So this will take you right to that implementation. You can also search for macros. In this case, when you search for macros, it goes, I know where this macro is defined, but I also know the macro definition already. So instead of also showing you where it's located, it will also just tell you what the actual macro definition is right in front of you. Finally, if you just type in a regular old search string, it will do a regular for-text search, like any good search engine will do. But it also goes, maybe you're trying to actually look for a function or a class when you just look for a simple string. So in the sidebar, it will also tell you these are all the functions which are called open channel. These are all the classes called open channel. These are all the macros called open channel. These are all the files called open channel. Anytime you can semantically determine that you're trying to look for that you might be looking for something else other than just a for-text search, we will include for you a link right there which will take you right to that definition immediately. So you never have to worry about so you don't have to worry about trying to find through all these uses to try and figure out what's going on. As I said earlier, one thing I also forgot to include on here is you can also search for callers of a function. So I can also search for everyone who calls open channel, and I can get a list of all the functions that call it. This includes functions that call it via dynamic reimplementations, via virtual method calls. Unfortunately, I don't have function pointer support working yet because that requires a lot more data flow analysis than just looking up a type hierarchy. As I said earlier, we originally used GCC, but then we switched to Clang. And the main reason we did that is because what Clang really gives us is it gives us extremely precise location information. If you do GCC, if you've got a function definition, it will just basically pick a location somewhere in that function name, which could be a few lines off if you've got a really long function name. And if you're just trying to locate the actual location, you have to resort again to scan the text, find the identifier, guess what it's actually referring to, which is defeating the entire purpose of doing semantic source code browsing if you basically have to resort to doing a grep all over again. With Clang, however, we can instrument the code and we can actually say, in between these three characters is the identifier that refers to the definition of this function. So I know exactly where to create the link to produce the link to this function name, and I also know exactly which function I'm looking at. Some other nice features of Clang. Clang's a lot cleaner to use for the preprocessor, as opposed to GCC, where it's a lot more hackish to have to hook into. And finally, we have a lot more accurate AST information. I don't have any examples off the top of my head, but I have known from experience that if you have template definitions or type defs, GCC will kind of throw away half the information before it gives you the AST. On the downside, there's some things that Clang still really sucks at. The biggest problem is Clang's plugin support is almost non-existent, and it's incredibly crappy and hard to work with. The only way I could get it to work was I found someone else's plugin online. I copied their code, the entire makefiles, until it worked, and I basically said, I'll use this, and I hope it works for everything else. I have heard by someone else who's tried to use this. I've not actually experienced it myself, but I have heard that it also creates problems with some other tools with the tool chain because the command line gets processed. They look at the Clang load and says, oh, you're trying to load a library in a compile time for the linker, and it completely screws up your command line all over again. So it can be problematic to use for other tools. Another thing that GCC has, which Clang doesn't have, is GCC generally works in most tool chains. Clang still doesn't work in most tool chains yet, and not all programs compile with Clang. Most open source programs, however, compile with GCC with no problems whatsoever. So just trying to work with Clang means you have to spend a lot of time also trying to filter out all of the compiler errors and trying to make sure your program actually compiles. Fortunately, it's gotten a lot better over the past recent months. At some point in time, the compiler error I constantly saw with Clang went away about a month ago and then came back somewhat for some other reason a few days ago. So I'm not entirely sure what's going on. The final benefit of GCC is that it has the Gimple API is a cleaner data representation, which is a lot easier to use for if you wanted to write your plugin in a different language. I originally said that DXR was built using the Dehydra plugin, which is a GCC plugin that reifies the type information in JavaScript. And JavaScript's got a cleaner standard library and is a lot easier to work with if you want to do pattern matching or stuff like that than trying to do it in C or C++, which is a crazy complicated scheme to have to write code for. And the fact that Gimple is effectively written in some form of S expressions basically allows you to run the compile, basically allows you to reify this information with very little trouble whatsoever. When I tried to do the same reification of the information similarly in Clang, I ended up having to write a compiler plugin to dump out all the information. And even then, it still didn't work about 80% of the time because I hit some random assertion, or I was just trying to grep for specific function names in the AST stuff, and the function names aren't all quite on the same naming scheme. DXR is not yet finished. It's still very much in the prototype stage. I'm sure some of you are going to want to come up here and ask me, how do I handle if-defs? The short answer is, right now, I don't. The goal eventually is to basically compile with multiple build options and basically combine all the results into a single database with notes on basically this function was included in this build option but not in that build option. So if you're on Linux, you only see this one, whereas on Windows, you'll see that one. We also want to integrate documentation, for example, the Doxygen support for everyone who uses Doxygen. We also want to do incremental reindexing. Firefox, building Firefox from, well, actually building my 4DXR from scratch right now takes about 2 hours. Unfortunately, a lot of that's because the disk it's on is really slow access. So we spend a lot of time just doing nothing but waiting for the disk to give us our data back. We also want to improve support for other languages. Right now, all we have is C, C++, and IDL. We would like to support Objective-C and JavaScript, primarily because about a third of Firefox's code base is actually written in JavaScript and not C++. Unfortunately, a dynamic language like JavaScript is a lot harder to code with, is a lot harder to deal with because it doesn't have a strict type hierarchy or it doesn't have strict type hierarchy or any other sorts of things that C++ does. It's a lot more dynamic language, which makes it a lot more difficult to try and understand what's going on. Right now, the source code is publicly available. You can go online, you can download it right now. It should be fairly easy to integrate with your project. You just have to edit a few lines in the configuration file and basically run a script which will set up your environment variable, sets up CC and CXX and compiles it and runs it for you, and then produce the output. We also have a live version of this, which is working with the Mozilla source tree that's available to anyone on the web right now. So you can actually go in and find this entire source code of Firefox using this. I also have been using this a lot more locally, so I have a full tree for LLVM and Clang on my computer, which isn't yet publicly available. Hopefully I should be able to do that as well. So are there any questions? Yes. For the most part, just it's almost instantaneous. If I were to go back to one of these slides, if I click on that, just to locate, if I have the info box, it basically does a query to look up the information. Just doing that takes, for this one, it takes about a few hundred milliseconds. For some of them that have thousands of references, it can take a few seconds. A lot of it also depends on the I/O performance of the thing, because SQLite is not particularly performant in terms of I/O. If you're actually doing a search, most of these searches are about equally fast. For text search can be slow. Sometimes it can be done in seconds. Sometimes it can take 20 or 30 seconds, depending on how many times it's included and also the current load on the server. Any other questions? Yes? Mm-hmm. Well, I mean, we basically instrument the compiler, so Clang already reparses the header files, and it can also be that sometimes header files, like in particular if you've got table generated header files, where basically it's just a giant list of macros, where you basically, before you call it, you set up what the macro definition is going to be. So each time you include a header file, it's got different macro definitions. So you still have to reparse it every single time. But the advantage here is that we just produce a lot less data. So whereas before my output data was on the order of 20 gigabytes, if I index by the translation unit, it's about 2 gigabytes if I index by the header files. There are still some duplicates, but there's a lot fewer duplicates. Yes. Yes. Well, so for the most part, because it's all hidden under macros, you don't actually really, if you've got like a function definition, it will list all the function definitions that happen in that file. But because it's all hidden under the macro, you don't actually see it. And right now, the macro definitions don't work. They only use one macro definition right now. I have to go back and actually add support for multiple different definitions of the same macro. Yes? I don't have any of that metadata yet. It shouldn't be too hard to add that in. On the build I have for Mozilla, I don't have the code coverage information because trying to run all that linearly on the same program would take about 48 hours, I think, at this point in time. So it's just completely not. I can't do it. But if you do have code coverage information, I can include that, and I can actually produce an index of it. I may have an example somewhere up on the web. I don't know if I've taken that one down yet, though, or not. Yes? So one of the things we have is you can actually download the entire database that's produced by this, and you can run that SQLite database locally with all of your queries. We also have some ideas to basically output a giant CTAGs file that has the locations of all of the information. So any editor that has CTAG support included could leverage this information at the same time. But as of right now, we don't have any specific tools that are integrating with IDEs yet. Any other questions? We have template support right now is a little bit wonky. It turns out that Clang's AST gets a lot funkier with templates, and until recently, Mozilla doesn't have didn't use a lot of templates because they were stuck with C++ as it was interoperably existed in 1998, as opposed to as now interoperably exists today. So the template support is a little weak right now. But eventually, yes, there are plans to support templates in a similar manner to macros. Yes? Well, as a basic, what you have to do is you have a configuration file, which basically says this is where the source directory is located. This is where the object directory is located. So if you include it in the object directory, it will automatically look for a file in the source directory or the object directory of the tree. So it does not take that much to get it to run on an object directory as well. I can, for example, do the generated code for LLVM in as many lines as I do the generated code for Mozilla. Well, right now, all that I have support for with code coverage is just supporting gcov's output. And even then, mostly it's primarily just limited to looking at the line coverage information because that's the easiest to display on an HTML page. Any other questions?